85% volumetric efficiency. So recalling, our EV is equivalent to V1 over VD. And we know that our V1 is also equivalent to mass times our specific volume at point 1, which is the entrance to our compressor. While the displaced volume of our cylinder is equivalent to the length of the stroke times the area of our cylinder times our speed times the number of cylinder and our factor K. Okay, so we have here a given volume and efficiency, that's 85%. We have here a specific volume, which is 0.592 cubic meter per kilogram. Our number of cylinder, according to our problem, which is a twin cylinder problem. So meaning we have two cylinders, so we have C. So this is single acting, so our K is 1. Our engine is running at 250 RPM, so we have a speed. And then according to our problem, our bore is equal to stroke. So meaning the length of the stroke is equal to our unknown, which is the diameter. And of course, our area is equivalent to the cross section of our cylinder, which is a circle, which is pi over 4 diameter squared. So meaning our area and our length are in terms of diameter. So that is our unknown. But we don't have yet our mass flow rate of the refrigerant passing through our compressor. So we must solve that first before finding the bore. So as you can see, we have here a capacity in our refrigeration system, which is 700 kilowatts. And we have here a refrigerant effect given per mass, which is 1,160 kilojoules per kilogram. Take note, our capacity QA is equivalent to mass flow rate of the refrigerant times our refrigerating effect. So meaning our mass flow rate is equal to capacity QA over the refrigerating effect. Okay, so our QA, or the capacity, this is a 700 kilowatt refrigeration system. So that's our capacity. Kilowatts or kilojoules per second. Divided by our cooling effect or refrigerating effect, that's 1160 kilojoules per kilogram of mass. Okay, cancel out kilojoules. So our mass will be in kilograms per second. Our answer here is 0.6034 kilograms per second. Then we can now use our volumetric efficiency formula. Okay, our EV is 85% or 0.85 is equal to, for our numerator, we have mass, which is 0.6034 kilograms per second. And our specific volume is 0.592 cubic meter per kilogram, divided by our length, which is also the diameter, area, which is equivalent to pi over 4 diameter squared. Our speed is 250 revolution per minute. So as you can see, our mass is per second, so our speed should also be in revolution per second. So this is 250 divided by 60 to make this revolution per second. This is a twin cylinder, so there are two cylinders. And this is single acting, so our K is 1. Okay, it cancels out seconds. So our diameter will be in meters. What is our diameter in meters? The answer is 0.400 meters. Or in millimeters, that is equivalent to 400 millimeters. The ratio of the average load to the peak load over a designated period of time is called load factor. Okay, we have here a cylindrical flash plant with axis horizontal. And this is filled with liquid ammonia. Okay, so the question here is, what is the diameter of this tank? Okay, so let's analyze our given. At this ammonia inside our tank, ammonia vapor disengaged to its surface. And that surface can be seen from our top view. So from our top view of the liquid ammonia, that is the surface where our ammonia vapor bubbles through. So as you can see, this section here is also the length of our cylinders, and that is 1.5 meters. And this section, let's say this is the width, which is the same as this section. Okay? So we have here an ammonia vapor, which bubbles through the liquid at 70 cubic meters per minute. So we have a volume flow rate at which the ammonia vapor bubbles through. As we all know, Q, or the volume flow rate, is area times velocity. And that area is this disengaging surface area. It's 1.5 meters times our width, which is still unknown at this point. And V here is our disengaging rate, which is given, and that is 60 meters per minute. So we have a given V as well as Q. And our area is length times width, which is 1.5 meters. That's our length. And our width is still to be solved. Okay, so what is that relationship of the width with our ano, which is the diameter? So let's see with our front view of the cylindrical flash tank. So as you can see, this is our diameter. And from the top of our circle up to this point, that is 1/3 of its diameter according to the problem. As the problem said, the liquid level is to operate with liquid level 1/3 of the diameter from the top. So that section from the top of the tank to its surface is 1/3. And we know from the center of our circle up to any point in our circle, that is the radius, or 1/2 the diameter. So as you can see here, this section is equivalent to the whole diameter minus 1/3 of the diameter minus 1/2 of the diameter, which is equivalent to 1/6 of diameter. So why is that important? Because as you can see, we can form a right triangle wherein 1/6 of the diameter is one of its length. And we know that this section from the center up to any point in our circle, that is also the radius, or 1/2 the diameter. And from earlier, I said that what is the relationship with our width and our diameter? As you can see, this section is 1/2 of our width because this point is this point. And up to this point, so that is equivalent to half of the width. And you can see here that this is a right triangle. So we can use the Pythagorean theorem. So the square of the hypotenuse, which is 1/2 of the diameter, squared is equivalent to the sum of the squares of the two other legs. So we have here 1/6 of the diameter squared plus 1/2 of the width squared. So this will be 1/4 d squared is equal to 1/36 d squared is equal plus 1/4 width squared. Okay, we can transpose here up to this point, so that will be 1/4 minus 1/36, so that will be 2/9 d squared. It's equivalent to 1/4 width squared. Okay, so we can cross multiply 4 here, so this will be 8/9 d squared is equal to width squared. And taking the square root of both sides, so our width will be equal to d times square root of 8/9. So we can put width here. So our Q is equivalent to 70 cubic meters per minute. It's equivalent to our area is 1.5 times width. So that will be 1.5 meters. And our width is equivalent to this one. And that's D times square root of 8 over 9 times our velocity, which is 60 meters per minute. It cancels out minutes as well as the 2 meters. So the unit of our diameter will be in meters. What is our diameter? The answer is 0.825 meters, or the same as 825 millimeters. The best answer is 830 millimeters. When a system deviates infinitesimally from equilibrium at every instant of its state, it is undergoing a quasi-static process. So we have here a power requirement for the compressor. So we know that the work of the compressor can be expressed as mass flow rate of our refrigerant entering our compressor multiplied by the change in enthalpy at the entrance and at the exit of our compressor. So this is our unknown, the delta H. So that is the ideal. So ideal meaning there are no heat losses in our system. But in this case, the compressor has a heat loss of 25 kilowatts. So this will be an actual process. So for our solution here, we will be considering the heat loss. Okay, so to find the delta H, that is the ratio of our actual work of the compressor divided by the mass flow rate of our refrigerant. Okay, so let's start with our ideal power requirement of 150, that's horsepower. So let's say we need the power expressed as kilowatts. So we know that 1 horsepower is 0.746 kilowatts. So that's the ideal. And of course, we need to consider the heat loss. So that's minus 25 kilowatts. So this is the ideal power, and we get the difference with the heat loss. So this is in kilowatts or kilojoules per second. And this will be all over our mass of our refrigerant entering the compressor, which is 0.50 kilograms per second. You can cancel out seconds. So our delta H is in kilojoules per kilogram. What is our change in enthalpy? This is 173.8 kilojoules per kilogram. When a substance in gaseous state is below its critical temperature, it is also called So as we can see, initially we have a 300 kilograms of ice at negative 4.4 degrees Celsius. But after 24 hours, it melts into 7.2 degrees Celsius water, meaning there is a changes in temperature and changes in phase that happened during the 24-hour period. So meaning this is a combination of sensible and latent heat. So that is the total rate of cooling. Okay, let's start with our mass of the ice, which is 300 kilograms. And the process is within 24 hours. Let's start with our sensible heat that happened on the water phase. So this will be Cp of water, which is 4.187. That's change of temperature of our water. So our water is at 7.2 degrees Celsius. And we will be minusing our freezing point, which is 0. Plus our latent heat of fusion, 335. And then for the sensible heat in our ice, Cp of ice is 1/2 of 4.27, that's 2.0935, times the change of temperature of ice, that will be our freezing point, minus negative 4.4. So within our bracket here, we have here kilojoules per kilogram. It cancel out kilogram. So our average rate of cooling will be in kilojoules per hour. What is our answer? This is 4,679.47. This is kilojoules per hour. The best answer, 4679.28. At the same pressure and temperature, equal volumes of all gases contain equal number of molecules. This is also known as the Avogadro's law. Okay, so we can see here our poultry involves changes in temperature as well as changes in phase above and below freezing, meaning the product load is a combination of sensible and latent heat. Okay, so let's start with our formula. So our product load, Q. Let's start with our mass of the poultry, which is 500 kilograms. And this process goes on for 15 hours. So multiplying this by 3,600 to make this seconds. Then let's start with the sensible heat above the freezing. So our Cp above is 3.80. Multiplied by the change of temperature above freezing. So initially we are at 8. And then minus the freezing point, which is negative 5. That will be minus negative 5. Plus our latent heat, 246. And then our sensible heat below the freezing, so our Cp below is 1.55. Times the change of temperature below freezing, so let's start with the freezing point, which is still negative 5, minus the final temperature, which is negative 18. And the unit inside our brace here is kilojoules per kilogram. Kilograms is cancelled, so the remaining unit is in kilojoules per second or kilowatts. What is our product load? This is 2.85 kilowatts. The number of protons in the nucleus of an atom